Hello everyone. In the last few lectures, we have been discussing about mud logging and different techniques that we use in mud logging and cutting analysis. For example, we have discussed about how to analyze the rock cutting for presence of hydrocarbon. For example, we know that when we drill any formation, the rock cuttings are transported by the drilling fluid through the annular up to the surface, where at the cell cycle they are collected and they could be analyzed for the presence of oil and gas. For example, we discussed that the fluorescent test can be used to know that whether the rock cutting have any oil or not. Similarly, the rock cutting can also be analyzed for visual presence of oil. For example, if you are drilling through a oil zone, oil stain might be there on the rock cuttings. Beside the presence of oil, we can also analyze the rock cutting for lithological analysis. We can know that what type of rock formation it is. For example, whether we are drilling through a sandstone bearing formation or a carbonate bearing formation or shelly formation or any other formation such as coal, anhydrite, etc. Today, we'll be discussing about some other types of analysis in mud logging such as analysis for gas, and also we will discuss about what are the different drilling parameters which we can analyze and how it can give us an idea about formation characteristics. In today's lecture, we will discuss some other analysis in mud logging. So after the analysis of drill cuttings and returning mud for the presence of oil, we can also analyze the returning drilling fluid for the presence of gas. So drilling fluid has certain gas inside it which we can separate at the surface, and then this gas could be analyzed to check whether this gas contain any hydrocarbon gas. So if you are drilling through a hydrocarbon bearing formation, maybe oil bearing formation or maybe a gas bearing formation, during the drilling of a hydrocarbon bearing formation, some gas will be deposited inside our drilling fluid. So when this drilling fluid will come to the surface, and if you take this gas out and you try to combust it, we'll see combustion because hydrocarbon gas can be ignited. So this way this gas could be identified. After that, we will also discuss what are the different drilling parameters, how we can analyze the drilling parameter, and what type of information they can give us. Thereafter, we will discuss a sample mud log and we'll see how these tests are performed and how this information is presented in a sample mud log. So starting with, we have already discussed how to analyze the cutting, then how to analyze the drilling mud for the presence of oil. Today we will discuss how to analyze for the gas and then analyze the different drilling parameters such as drilling rate, pump rate temperature, wet on bit, and mud properties. So during drilling, when the gas comes out at the surface, at the cell cycle, the cuttings are separated and there is a gas trap. This gas trap separate the gas which is coming out of the drilling mud, and then it is sent to the mud logging unit. Mud logging unit is present at the surface where the instruments are kept to analyze the gas from the drilling fluid for the presence of hydrocarbon. So what type of analysis we do for the returning mud? We can have two types of analysis. One is called total gas analysis and second is called the component analysis. The total gas analysis, in this type of test, what we want to do is that we want to measure the total amount of gas or the hydrocarbon gas which is present inside the drilling fluid. So once the gas is separated at the surface and it is sent to the mud logging unit, we will perform the experiment to know that how much amount of hydrocarbon gas which could be ignited is present inside our returning gas from the drilling fluid. So what happens is that if you are drilling through a oil zone, the oil will come inside the drilling fluid. So when this drilling fluid moves up, the pressure decreases and gas will come from the oil. The oil will liberate some amount of gas. So the now drilling fluid will have some hydrocarbon gas inside it. So this will be detected in total gas analysis. Also, if you are also drilling through a gas bearing formation, then the gas bearing formation will bleed some gas inside the drilling fluid. So again some hydrocarbon gas will be there inside the drilling fluid, so which could be analyzed. So in total gas analysis, we want to measure how much amount of combustible gas or hydrocarbon gas which could come from a hydrocarbon bearing formation is present inside our drilling fluid. So this instrument is many times also called the total hydrocarbon analyzer THA, or many times in the mud log you will see this will be written as total gas analyzer or TGA. So generally TGA measurement unit is represented as the total methane equivalent or TME, which is the BTU content of the gas extracted from the drilling fluid, expressed as the which could be obtained from an equivalent concentration of pure methane in air. So basically how we are comparing is that whatever the energy we are getting, how much concentration of methane will be needed in air to get the same amount of energy. So this way these two concentrations are compared. So in the mud log, you will see that total gas analysis result. It will written as total methane equivalent, which is nothing but it is the BTU content in the gas extracted from the drilling fluid, expressed as that which would be obtained from an equivalent concentration of pure methane in air. So at the surface, we could have different type of instrument to have total gas analysis, which could be the flame ionization detector or hot wire analyzer or thermal conductivity detector also. Second analysis is called the component analysis, where we are not only interested in the total amount of combustible gas, but also we are interested in the what is the individual concentration of different type of gas in the returning gas. So we know that hydrocarbon gas or hydrocarbon could be a number of components. For example, different hydrocarbon component in the returning gas could be C1, such as methane, C2, ethane, C3, C4, C5, and so on. So we want to know that what is the individual concentration of all these individual compound in the returning gas. So we can use gas chromatograph or mass spectrometer or infrared spectrometer or any other instrument at the well site to analyze the component of returning gases. So here we have mentioned that what are the different types of instruments that we use for gas analysis. One is the catalytic filament detector that is used for the total gas analyzer. Then thermal conductivity filament detector or the hot wire analyzer. This is also used for the total analyzer, the total gas analyzer. Then the flame ionization detector that also used for our total gas analyzer. Gas chromatograph or mass spectrometry can also be used for our component analysis. Before we analyze the returning gas for the presence of hydrocarbon gases at the well site, we must also note down the what is the background gas concentration inside the wellbore. So some other sources might bleed some small amount of hydrocarbon gases which might be present inside the returning gas. So a background gas concentration will be recorded, and any increment from the background gas concentration will be treated as the presence of additional amount of hydrocarbon gas which may have come from a hydrocarbon bearing formation. This level of background gas concentration may be very small, from few ppm to slightly higher percentage depending upon the circulating condition and what type of formation that you are drilling. The primary tool for analysis generally at many other well sites is a flame ionization detector or the FID, which could be used to detect the hydrocarbon gas even as low as concentration from 5 to 20 ppm. In terms of ppm, 10,000 ppm is generally equivalent to 1% of methane or 50 methane equivalent units. Before we move further, I just want to show you the mud log example, how this data is represented in the mud log. For example, you can see here we have a total gas unit where the total gas analysis has been presented. You can see these are the background concentration, and wherever you have a peak, that means additional hydrocarbon gas has been detected at the surface in the gas analysis that has been represented in terms of total methane equivalent. So you can see here it is increasing, total gas units are increasing. Here also it is increasing, here also it is increasing, here also it is increasing, here also it is increasing. Not all of them are indication of a gas bearing formation and oil bearing formation. For example, in this mud log, only this peak is indication of a hydrocarbon bearing formation. We will discuss at the end of this lecture why this is the case. Before that, we need to discuss few more concepts related to this. In the second track, you can see we have the chromatograph reading where the for individual molecules C1, C2, C3, C4, C5, the concentration has been recorded and presented. So individual gas concentration is presented. You can see also there is a column for fluorescence. Right now there is no fluorescence test has been successful in the well bore, so nowhere it is recorded here as a positive fluorescence test here. If there was a positive fluorescence at any well depth, it would have been mentioned in this track. This is how a flame ionization detector works, and this is a sketch of our gas chromatograph. The working of flame ionization detector and the gas chromatograph are not in the purview of this course. If you want to learn more about how these two tools works, you can look in the to Google or different online sources, or you can find out in different books also. Now, we can also quantitatively analyze the result of our gas chromatograph data. For example, we can define three ratios. First is our gas wetness ratio GWR. Second is our light to heavy ratio LHR, and third is oil character qualifier OCQ ratio. So GWR ratio is defined as the amount of C2 plus compound divided by the how much amount of C1. Similarly, light to heavy oil ratio LHR is it is the ratio of Cm plus C2 divided by C3, C4 plus C5, and OCQ is defined as C4 plus C5 divided by C3. So in a gas bearing reservoir where the formation contains gas, their amount of C1 compound will be maximum. But if you have an oil reservoir, then the gas which will be detected inside the mud, it will have more concentration of C3, C4, C5 and C2. Predominantly gas might be, the main constituent might be C1, but in case of oil reservoir, the gas will also have higher concentration of C2, C3, C4, C5 compound. So these qualifiers can be used to identify whether we are drilling through a gas bearing formation or a oil bearing formation. For example, if you see the gas wetness ratio, if you see we are going from gas to oil reservoir, the gas wetness ratio is increasing because C2 compound and C2 plus compound concentration and or the mass will increase. So obviously the GWR ratio must increase. Similarly, LHR, going from gas to oil, the ratio of light to heavy ratio or LHR is decreasing because if you go to the oil reservoir, this amount of or concentration of C3, C4, C5 will increase and C1 and C2 will decrease. So LHR is decreasing. Similarly, OCQ is increasing because if you move from the gas to oil bearing formation, amount of C4 and C5 will increase. That's why OCQ is increasing. Now, as I mentioned earlier, not all amount of gas shown in the total gas analyzer result could be indication of that we are drilling through a oil and gas bearing formation. There could be certain sources which may bleed off some gas inside our drilling fluid, but they may not be a oil and gas bearing formation. For example, we can identify the gas show in a number of types. So gas show is nothing but the presence of gas at the surface in the gas analysis instrument. So when we analyze returning gas from the drilling fluid at the surface, if you detect any gas, this is called a gas show. So there could be a number of gas show sources. For example, they could be liberated gas, produced gas, recycled gas, contamination gas and connection gas. Liberated gas is nothing but the gas mechanically liberated by the bit as the formation is being drilled. So this is a true gas show when we are drilling through a oil and gas bearing formation. So the gas is liberated and it is mixing with the drilling fluid which is now at the surface detected. Produced gas, so the produced gas is the gas which is produced due to underbalance condition. For example, this is a gas pay zone. So we are doing the drilling in overbalance condition. Right now our drilling bit is here, but since the pressure is greater than the formation pressure, that means well bore pressure PW is greater than the formation pressure, the gas will not come inside the wellbore. But if a underbalance condition is created, what will happen? The gas will start to come out and it will move up and mix with the drilling fluid. So this may happen during the connection assembly, during nutrition assembly. A slight underbalance condition might be created for a very small duration of time, and some gas might come inside the wellbore and mix with the drilling fluid. Next source could be the recycled gas. That means gas which were already inside the mud. Maybe the produced gas during the drilling. When it came to the surface along the drilling fluid, so the well site equipment such a degasser, they were not able to properly remove all the gas from the drilling fluid. So what will happen is that the drilling fluid will contain some amount of gas, and when the drilling fluid is again reinjected, the gas will again go inside the wellbore, and when the drilling fluid is again will come back to surface, same gas will be again detected. So in many times what may happen if the well site equipments are not handled properly or they are not operated properly, some gas might remain inside the returning drilling fluid, it may not be removed. So when the drilling fluid is again recirculated, we will again detect the same gas. So recycled gas can also be a source of gas show in our drilling operation. Next is contamination gas. So contamination gas is nothing but the gas which is artificially introduced into the mud from other sources. For example, this could be mud additive or tracer. For example, we have discussed about the carbide test in the depth matching. So a carbide test, we introduce the calcium carbide nuggets inside a pouch and when this calcium carbide reacts with the drilling fluid, it creates the acetylene gas. So this acetylene gas will be detected at the surface, and this should not be taken as an indication of the hydrocarbon bearing formation. Next is connection gas. So during the connection and trips, the reduction in the bottom hole pressure, as I mentioned earlier, may cause a temporary underbalance condition. So connection gas may be present at many discrete interval. So whenever doing tripping or changing the drill pipe connections, underbalance conditions are temporarily created due to pump shutdown or the pipe movement. So often you will see on the mud log, wherever a pipe connection has been made, some small peaks of the gas will be there. These small peaks should not be taken as the gas show from the hydrocarbon bearing formation, whether as this should be taken as a connection gas show. For example, typically you can see here in this figure, this is the background concentration. You can see the background concentration of the gas. This is the actual gas show. This is a connection gas. This is a carbide test gas. This is trip gas. So during tripping, some gas were introduced. So this is trip gas. This is your connection gas, and this is your carbide test gas show. So these are the common gas show types: the gas show from actual formation, the connection gas, the carbide test, drip gas, and the background gas concentrations. So let us analyze the drilling parameter. Drilling parameter analysis can also give us a lot of information about the type of formation being drilled and the fluid it may contain. Generally, the most of information could be interpreted in terms of rate of penetration. So during drilling operation, we continuously analyze the rate of penetration or the rate of drilling. At what rate we are currently drilling at the well depth. So rate of penetration can be analyzed in terms of drilling break or reverse drilling break. So a drilling break is nothing but a sudden increase in the rate of penetration or rate of drilling. So if we analyze the rate of penetration or the rate of drilling, at what parameter it is dependent? The rate of penetration or the rate of drilling is dependent upon the operational parameter and the rock characteristics. So operational parameter means our drill string design. So what is the width on bit? What is the rotation? Or what is the, if you have a motor bit, so what is at what RPM the motor is rotating? So width on bit, how much surface mud pump pressure that we are applying, the length of the casing string and drill string. They are all operational parameter which controls our drilling rate. Apart from that, rock characteristic also plays an important role. If you have a hard formation, the drilling rate will be slower. If you have soft formation, which is unconsolidated or loosely consolidated, or it has less cementing material, it will drill faster. So a hard formation will drill slower, and a soft formation, which is weak formation, will drill at a faster rate. So if porosity is increasing, generally its strength of the rock will decrease. So it will be easier to drill a porous formation compared to a non-porous formation. So if rate of penetration is increasing or the drilling rate is increasing, this may be indication of that we are entering in zone where porosity permeability is increasing, or also there could be change in pore pressure. So delta P has changed. So because of that, our rate of penetration has changed. So if all the operation characteristics are constant, that means our weight on bit and the drill string designs are constant. We are applying the same pressure from the surface, we are maintaining the same fluid or the drilling fluid injection rate, then the rate of penetration should be dependent upon our rock characteristics. In that case, a change in the rate of penetration, if the rate of penetration is increases, it should be taken as indication of our change in the rock type, and we are entering from a low porous formation to a high porous and permeable formation. There could be a reverse break also. So that is called the reverse drilling break, where instead of increase in rate of penetration, the drilling break have decreased. So it may be indication that we are entering into a hard formation, or it may be due to a problem with our bed. So drilling break is not only useful for the differentiating between a porous and permeable formation, or finding out if you are going to enter a potential porous and permeable formation which may contain hydrocarbon. It is also useful in our planning the drilling activities. For example, if we are entering a porous zone which may contain hydrocarbon gases or oil, then we might need to increase our mud weight. So whenever you see a drilling break, and if it is gives an indication of a porous and permeable formation, the driller at the well site, he might stop the drilling, and he will separate out our well bore, and he will take mud sample, he will take the cutting analysis and analyze for the presence of hydrocarbon. If he encounters a hydrocarbon zone, he will take additional precaution before drilling further. If a good oil and gas zone is found, the well site, the driller may decide whether to go for DST operation, or he may decide to do coring operation. So decision on the coring may be taken on the basis of the drilling data analysis to take core sample, which could be analyzed to give you an idea about the porosity and permeability of the formation. As I mentioned earlier, the rate of penetration or the drilling rate is dependent upon our drill string design as well as the formation rock characteristics. So an increase in rate of penetration or the drilling rate should be taken as indication of entering into porous and permeable formation only if the drilling parameter or the drill string design parameters are constant. But many times they may change during the course of drilling. So what are the drilling parameters at the surface? It will be different from the drilling parameter which is now currently at the bottom of the well bore. So during the drilling, bit on bit keep on changing. We may need to change the rotary speed or the mud weight also. So it is better to use the de-exponent data which is used during the drilling operation to know about our drilling characteristics. So whether we are drilling at lower rate or faster rate, it could be better represented in terms of de-exponent data. So de-exponent data is defined as log of R divided by 60 into N divided by log of 12 W divided by 10 to the 6 multiplied by D, where R is the penetration rate, N is the rotary speed, W is the bit on bit, and D is the bit diameter. There are some other modified de-exponent data also used nowadays, which also takes into account the bit wear and tear conditions. So de-exponent data may be presented in the mud log along with the penetration rate to take into account our change in the drilling operational conditions. Now let us come back to this mud log example again. Now we have discussed all the analysis which we do in the mud logging. So analysis for presence of oil, or analysis for presence of gas, or the analysis on the cutting, this all we have discussed. Now we should be able to understand the information printed in the mud log in a better way. So in this mud log, the casing was set at 7580 feet. So this is where the casing was set. Drilling rate of penetration after this depth was around 25 to 30 feet per hour. So you can see here, this is our rate of penetration. So it is somewhere here, it's around 25 to 30. Now, a trip of new bit in this well at 7650 feet resulted in 1548 unit of trip gas. So you can see here, there is a gas show. So as I mentioned earlier, not every gas show should be taken in the indication of drilling through a porous impermeable formation which may contain hydrocarbon. Here, during tripping operation, some underbalance condition might have been created which led to some bleeding of gas inside our drilling fluid and which is now detected at the surface. So this is not a gas show from hydrocarbon reservoir, and you can see in this figure it is mentioned as trip gas. We can also see at 3 other locations connection gas, this is connection gas. So even a pipe connection was made, some gas was momentarily introduced inside the drilling fluid. As soon as the drilling was started, no more gas was introduced. So small peak of gas during the connection of new pipe are mentioned here in this mud log. So this is not indication of hydrocarbon or gas bearing formation. Now if you see further at around 7890 feet here, there is a change in the drilling rate. The rate of penetration is increasing. So this could be classified as drilling break. So a drilling break is an indication of that we may be entering a porous and permeable formation. Now this is just an indication. A drilling break is just an indication that we may be entering a porous and permeable formation. Now this can be further confirmed by the analysis of gas and oil. You can see that here sand content has been increased. This one is sand. You can see sand content have been increased. That means it is sandstone bearing formation which may be a porous and permeable formation. It might have substance porosity and permeability. Now you can also see that here a large amount of gas was also detected at the surface. So this is a clear gas show. So coupled with a drilling break and a sandstone bearing formation plus gas show. These are very good indication that it is sandstone bearing formation. Drilling bed indicate that this sandstone formation is porous and permeable, and gas show indicate that it might contain some hydrocarbon. Now you can see that in the fluorescence test there is nothing mentioned. Nothing is mentioned here that any fluorescence was observed. And you can see in this comment section that no fluorescence is mentioned. So it is very likely that we are drilling through a gas bearing formation, but it may happen that it may be an oil bearing formation and the fluorescence may not be detected at the surface. Sometimes, especially if you are drilling through light oil reservoir, the fluorescence may not be detected at the surface in the fluorescence test. So it may be oil bearing formation or it may be gas bearing formation, but it is most likely to be gas bearing formation because indication is that we have very high amount of gas and no fluorescence is observed. So this was all about mud logging. We have discussed about different types of procedure that we carry out in the mud logging, such as analysis of cutting, analysis of oil, analysis of gas, and how this information can help us in finding out the potential location of hydrocarbon bearing formation. In the next class onwards, we will discuss about coring and core operations.